Streaming. Okay, excellent connection. Sounds good. Hello. Copy. And let's go to Discord, Electrical Engineering General, new, Control V. Okay. So, I gave you some homework. I hope you noticed this in the channel Electrical Engineering exercises. So do you have any questions concerning these exercises? Yeah? Okay, so that's a good question. So one of the students had that was, which example was it? This example, question 2? Yes. Example 723. So let's have a look. Bitte? It depends on you, whatever you like. Okay, that was example 7. Potential energy. So it was this example where you have 4 charges and you are adding these charges, so you're bringing them closely together. It was this example here, right? Okay, so then the question was, why doesn't, so the student asked, why doesn't the distance, why isn't it squared in this example? Because when you look at the Coulomb's force, right? So F is 1 divided by 4 pi epsilon 0 times, let's say, the field generating charge, your test charge, divided by r squared, and then we have r hat, right? And you remember, when we go to the potential, so the potential energy W, this is the question, right? What this always implies is that you have a force and you are acting against the force over a certain distance ds, right? And then we define this to be negative. Here we need this negative because we said that the work should be positive if we act against the force, opposite of the force, right? So in general, we would also integrate because the force might change over the way, right? That's the case here, right? You see, when you have, let's say, a charge, a positive charge Q, which generates the field, let's say, are you sure you can see from there on that screen? I am not sure. Yeah, okay, cool. So then you have here the electric field E, right? and then you have maybe here another charge, let's say another charge Q, and there is a repelling force which is dependent, of course, on Q, and on the distance r. Right? Where you have the distance vector between these two charges r. I think this is clear, right? So again, the force is repelling, so that means this charge here drives the other one away. And now what you do is you act against this force, and you have a little displacement ds, right? You move this charge a little distance, a little displacement, so small ds, right? A few millimeters in this direction, right? Then you are acting against this force in the opposite direction, and we say, okay, this is positive. So why do we have to take this into account? Why couldn't we just say, okay, this is F times the displacement S? This is only true if F doesn't depend on S, right? Or on the radius or on the position. But it's dependent on the position, right? Because you know that when you are getting closer, what happens to the force when you are getting closer? It's increasing, right? So that means when I'm here and I shift so I displace the charge again by a little ds, then I have to apply more work to do the same action, right? And then it's increasing and it's increasing. So I have to apply more and more force and act against a stronger and stronger force. So, but if you look at the units here, right, you see that the force, there's something like, so we for example said, what happened if we displaced, let's say from point 1, let's say from point 1 to point 2, F, which is dependent on R, right? F is dependent on where you are in your space. And now this ds, this displacement, the one we choose now, is we say, okay, our displacement is in the direction, so it's parallel to r, in the direction of r, and the absolute value, so the magnitude of our displacement is dr, which means, so for example, when you have your charge q, which generates a field, then this is a radially symmetric field, of course, right? And we could, if this here is our other charge, our test charge q, we can move it in any way, right? This could be our S, the path S we are following, right? Let's say we move it like this through the field. But in this case here, the easiest basically way is to directly move this charge against the center of the field, which means that our displacement, our tiny infinitesimally displacement step is, because here you have this r, right, is then r hat ds, dr, right? So we have here, and we are in the opposite direction basically, right? dr minus dr ds, right? So that we would have here the force, and then we have r dr, and let's say with the minus we get a plus here. And now if you look at the force here, you see that the force is, so that is the integral from point 1, so here's point 1, right? And we want to go, let's say, to 2. So we have a lot of tiny little ds's we have to follow, right, from here to here, right? And that's 1 divided by 4 pi epsilon 0. Okay, I could have taken this out of the integral, of course. QQ, and now look at this, right? We have r squared here. Then r dot, right? This is the direction of the field. This is the opposite direction of our displacement, dr. And what is r dot r? 1, exactly, right? So because this is the scalar product, right? So the scalar product between two vectors would be, so in general, so the general formula is, let's say, A vector dot B vector is magnitude of A times magnitude of B times cosine phi, which is the angle between the two vectors, right? So one vector here, another vector here, A and B, and we have a vector phi here. So, and since they are parallel and the length is 1, right? So if you replace them now, so the length of our hat, it's the unit vector in direction r, that would be 1. This is also 1. And the cosine, since they are parallel, is 1 again, right? So it's the length, basically. You can also say this is the square of the length of the vector, right? So now this cancels, easy. And now we get a scalar w here, right? And you see now that you have to integrate this function 1 divided by r squared dr. And therefore, what follows is you get a antiderivative which looks like minus 1 divided by r. This is the reason why you have this 1 divided by r. Let me change to the screen again. So you start here, so you set in the beginning, that's your definition, right? No work, and you say my potential energy of the system is 0. That's what you define, right? You always have to start from a point, from somewhere. And you can say, okay, this is I just have one charge, and the charge alone does not have a potential. I say the potential of my system is 0. And now I'm adding another charge, I'm approaching another charge. And here you see, right, the W2, this is what now is added energy, joules are added because you do work in the system. You bring these two charges closer together. And therefore you have this charge 1, Q1, Q2, divided by R12, which is the distance between the two, right? So you start with one charge, and this charge doesn't have a potential energy. You say, that's your definition. You say, okay, my potential energy is 0, right? Like, what's the potential energy of my purse? When it's on the table, it's 0. No, if it's on the floor, it's 0. No, so it's your definition, right? You say this is 0, and I add another energy by doing work, and then I release it, and it falls back, and then it's again at, let's say, my 0 level of energy. So now you bring this closer together, which means you have to now, okay, you have these constants here, which is the 1 divided by 4 pi epsilon 0, right? It's in front of this k is 1 divided by 4 pi epsilon 0, q1, q2, and the distance between the charges. And then you're substituting this, right? Okay, so far so good. So you basically, and they are repelling, right? So you have loaded the system already with energy, potential energy, because they want to repel each other, right? And you keep them there. Right, it's loaded like a spring. You store energy in the system. And then the next one is, okay, now you bring another charge close to charge 1 and to charge 2, which means now you have to take into account the interaction of this charge with that charge and this charge, right? So when you add it here, you have basically the distance 1 centimeter between these two charges. And what's the distance between these two charges? Square root of 2, right? Because it's a right angle, a rectangle, and with the two cathetes being 1, and then of course this length here is then the hypotenuse is then square root of 2, and so on, right? And then you add another charge and so on. So you're adding more and more energy in the system. Okay, cool, good question. But you can see this also. This is maybe also worth to be mentioned. When you look, for example, right, this always looks really crazy, right? Also this one here. But it's not that bad. First of all, we have many cases where, for example, f is constant, or f is a simple function of the displacement. For example, when you have a spring, right? If you have a spring, the mass m or something, right, and you're pulling on this spring, right, then you can show that the force of the spring is negative, the spring constant times the displacement x, right? So here you see f is proportional to x. Here, let's say in this case here, right, magnitude of F is proportional to 1 divided by r squared, right? Sometimes we have constant forces. For example, a constant force would be in a constant electric field. You know that, so for example, Coulomb states, right, the magnitude of the Coulomb force is proportional to 1 divided by r squared. A spring, let's say the spring force is proportional to the displacement itself, x or s, whatever you call it, right, whatever you want, right, delta s basically. It is delta s measured from from an equilibrium point. Then we have, for example, an electric field, a capacitor, a homogeneous electrical field, like in a parallel plate capacitor. It looks like this. So you have two metal plates, which are, so the distance between them is much shorter than the area, than the typical size of the plate. So usually you would say, okay, they're much longer, right? Not just that short. Then you have pluses here, for example, let's say plus 5 Coulomb on this side, negative 5 Coulomb on the other side. And then you have an electric field, and this electric field, so you have also stray fields here, but inside this capacitor you can assume that E of, let's say, your position X or R, whatever you call it, is constant, right? So, and I hope that you remember that the electric force on a charge is the electric field times the charge itself, right? This is how we defined it, right? So if you remember, if you look at the Coulomb force, 1 divided by 4 pi epsilon 0. So let me rewrite this. This is the source of your field. This is the distance between two charges. That is the direction of the field. And then you multiply this with Q, right? Usually you would put the Q here. But then if you write it like this, you can say, okay, that's the effect. This is the quantity, this is the principle which acts on the charge Q. And this is what we call the electric field, right? Okay, and always, and if you look at this integral, for example, right, then W is this is always true for all of these forces, right? It's a general principle. When you act against a force over a certain displacement S, right, from, let's say, point 1 to point 2 or so, if you look at the units here, you will see that that you can multiply these units, right? You can say the units of F, for example, is Newton, which is kilogram times meters per second squared, right? Which is in Newton. Mass times acceleration is a force. And of course, the unit of ds, the d just means it's a little tiny distance, right? It's of course meter. Even if it's a vector, right? You have several, let's say several components, but in each component you have this meter unit, and we talked about this. You can multiply the unit to the components, right? For example, if you have a vector, let's say r, with the three-dimensional vector, then you can write it like this: 1 meter in x direction, 2 meters in y direction, 3 meters in z direction, right? So this unit is like a multiplicative constant. So you can take it out of the vector as a scalar, or you multiply it into the components, right? Okay. So, and then you see, okay, then of course the unit of W now in this example, right, is then Newton times meter, or kilogram times meter squared divided by second squared, which is joule. So you see the integral doesn't change the units. It's just a sum, right? It's like a sum of tiny little products, right? A little f, a little ds, right? And you're multiplying them and then you're summing them up. That doesn't change. this integral doesn't change the units. So you can derive the units of the integral directly by looking at the integrand, so what you integrate. Right? That's it. Not so difficult, basically. Right? You have to get used to it, but at some point it becomes totally clear. Right? It's like a osmosis, right? You need to expose yourself to this for some time in a certain concentration, and then it diffuses through your brain. Okay, so do you have more questions concerning the exercises? And the one here, that was a bit weird because I tried to motivate. Where am I here? No, this one. So here I try to motivate higher dimension vectors. Is this concept clear? Okay, cool. Because you can imagine that, for example, if you have vectors in 3D, right? So if you have vectors in 2 dimensions, it's easy to determine an angle between these 2 vectors, right? If you have these vectors in 3 dimensions, they're somehow oriented. But what you can do is basically you can define a plane here, and then you can measure the angle in the plane. So that also works for 3 dimensions, right? And of course, if you have 5 dimensions, which we cannot draw anymore, you could still define a plane which is spun by these 2 vectors, right? And then you can also measure an angle in a 5-dimensional vector space between 2 vectors. Do you understand what I mean? So if you have 2 vectors, right, in 2D, it's clear they live in this plane. If they are in 3D, somehow oriented, right, you can still define, so 2 vectors, if they are not collinear, they are spanning a new plane, right? You can find, even this is an embedding of, let's say, a 3-dimensional plane, which in fact is 2-dimensional, right? If you just turn it, and the plane itself is 2-dimensional. And then again, you can look at the angle. And you can do this even in 5 dimensions. So even if you have a 5-dimensional vector, 2 5-dimensional vectors, they still have an angle. And the closer, so the closer the cosine becomes 1, the more similar they are. This is what people are using in so-called word embeddings in large language models. So words are represented in series of numbers, right? And you can think of this series of numbers being a point in a vector space. And they can be very high dimensional, 700 numbers or so, representing one word. And then you have another word, another 700 numbers, and another word, 700 numbers. And then you can determine the similarity of these words. This is how these language models work. So this is one of the principles. So this is fundamental for, I tried to explain this here. Okay, anyway. Good. So then some other questions here as well. So today I would like to continue with voltage and current. And so let's summarize a little bit what we have found so far. And you have to help me a bit. So we said, what's the relationship between the electrical force and the electrical field? So where does an electrical field come from, first of all? Yeah, from a charge, right? A charge is the source of an electric field. Okay, so then now let's abstract it, and we are just looking at the fields and not at the charge anymore. What is now the relationship between this field and the force which is exerted on another charge I bring into this field?
Is it supposed to be, is the force equal to the electric field multiplied times the charge?
Absolutely, absolutely. So we have the force is the electric field times Q, right? For example, when you have these 2 parallel plates here, you have an electric field. You don't have to know about the charges on the electric on the plates. You're just interested in the electric field. This is enough. Or you have a point charge, right? This star thingy. You say, I'm just looking at this electric field, right? Forget the charge in the center. So this is the electric field, which is given somehow, right? And then I have another charge here, which is my Q. And then this electric field acts on a charge and exerts a force on it, right? Good. So then we had this potential energy, in general like this. And for the Coulomb force, we can write it like, so the potential energy would be 1 divided by 4 pi epsilon, this is a 4, this is a pi, epsilon 0 q divided by r, right? And of course this is a scalar, it's not a vector anymore, right? Joules don't have a direction. Good. So then we said the potential V. This is the potential energy per your test charge Q. Right? So the potential for a point charge, in this case, would be for a point charge, right? We are talking about this point charge. And of course, right, it's radially symmetric, and I'm too lazy to draw all the arrows. Of course, here, right? I think it's clear, right? It's isometric, and I say isotropic. So V is then 1 divided by 4 pi epsilon 0 Q divided by R, right? Okay, so then we have a potential difference, delta V, which means this potential difference basically drives charges. And now we come to the electrical current. So let me see if I can find this, what I wanted to tell you. No, here. Current and resistance. Yeah. Here. Screen. So I didn't prepare slides. I'm just taking the images and the figures directly from the book, right? I think that makes sense. Let's assume this is a piece of wire, let's say a metal wire with free electrons and charges can move. But this is general, right? So whenever you move charges across an area, right, over time, you call this a current, electrical current. So and the definition is basically, so you have here some tiny, let's say, elementary charges, right? And these elementary, like electrons, for example, electrons moving through this area. And then the amount of electrons or the amount of charges transported by the electrons through the area per time is what we call a current, which means it's the change of, or the transported charge, not just by one particle, but you have, I don't know, 10 to the power of 23 particles or so, moving over a certain time through a cross-section. This is what we call the electric current, right? So, and in general, this might change over time. For example, you see this here. This is a charge which is transported. So this is a charge over time. That we will see later that this is the charging curve of a capacitor. So what you can see is there is something which collects charges. It collects charges. So it's like a bucket, and we fill this bucket with charges, right? And how many charges we fill in per time, the rate of the transport is what we call the current. So you see that this bucket now is at one place it's full, then we have the maximum possible charge of this bucket, and you see that this changes over time. So where do I see here the current? What is the definition of the current again? Flow of charge per what? per time. So it's the rate of charge transport. So what would be the unit? Ampere, that's correct. But we don't know ampere yet. How can you express ampere? What is the unit of charge? Coulomb per second. Coulomb per second, right? Here we see coulombs. And we said that I is the transported charge over time, right? But Q changes with time. And then we say, okay, because Q isn't constant, so delta Q is not constant, delta Q over delta T is not constant. Where is this here? Here, right? So delta Q over delta T might not be constant. Sometimes we have 1 ampere, right? 1 Coulomb per second, that's constant. But in the case of when you charge a capacitor, the rate of change, the rate of transported charges into the capacitor declines, decreases. So that means at some point it's full. So when this changes over time, what we have to do here basically, we have an instantaneous current at a given time. And this is then what you do is you basically shrink the time span, right? I have my stopwatch and I'm measuring from T1 to T2 and I measure, okay, from T1 to T2, I have 1 Coulomb transported. And let's say from T1 to T2 it might be 1 second. That would be 1 Coulomb per 1 second would be 1 ampere. But sometimes the current changes over time. What we then have to do is basically we have to shrink the time span to measure the current. For example, let's say so we said I is first of all delta Q divided by delta T. So how do I see that? For example, if the transport Q, right? Let's say if we have a constant current, so for example, then Q over T would look like this. Why? Because I can take, let's say, I take here equidistant times, let's say T1, T2, T3, T4, and I'm measuring the Q's, right? So up to this point, I have Q1, up to that point, I have Q2, up to this point here, I have Q3, and so on, right? Should be equidistant here. I don't know, something is crappy, okay. I don't know why. Anyway, so, you know, so for example, from here to here, we transported, what is the difference of the charges we transported between 1 and 2? That's Q2 minus Q1. And the time? T2 minus T1, right? And this is what we call the current between, let's say, the time interval from 1 to 2, right? And this is delta Q divided by delta T. So, and here, I3, right, is then delta Q from 3 to 4 divided by delta T from 3 to 4. So basically T3 minus T4 minus, so let me rewrite this. So it's Q4 minus Q3 divided by T4 minus T3, right? And if they are constant, so it's obvious that this is the slope, right? This is our delta Q, this is the delta T. This is the delta Q, this is delta T, right? It's the slope of this triangle, right? The slope of the triangle is our current. It's the first derivative you can think, right? So in this case, they are identical because we say the current is constant, which means the triangle doesn't change over time. But in the other example, it looks like this. And then it makes a difference whether I measure here or if I measure here. Right? Let's say we have here T1, T2, T3, T4. Let's say the delta T can be the same, right? Let's say this delta T is the same. So we choose these times that we measure. So we measure for 1 second, for example, right? We have our stopwatch, 1 second, delta T is 1 second, right? From, I don't know, from 15 o'clock, 13 minutes and 13 seconds to 15, 13, 14 seconds, right? And then later we measure at 15, I don't know, 27, what is it, 3 to 15, 27, 04, right? So at different times, the same time difference, 1 second, right? So delta T is 1 second, and later it's still 1 second. Okay, so this is 1 second, and this is 1 second. And now you can see that delta Q, let's say for the case, how should I call this? From 1, 2, let's say, and here delta Q 3, 4, they are different, right? Here we are transporting, this is of course Q again, we are transporting different amounts of charges, right? This is then Q3, and this one here is Q4, right? So that means this is still okay-ish if delta T is small. And then you have basically a local, so the question is, what is the slope, right? You say, okay, it's this slope. And this slope here is an approximation for my, I don't know, for my current at this time. And this slope here is an approximation for my current at this time, right? So this is only approximate. So this is only approximated. But what we can do is we can say, we let these triangles shrink and say, okay, we drive the delta T to 0, which means what you do is you're making it smaller and smaller and smaller, and then your approximation becomes better and better, or in the other direction, right? You move, let's say, this point here to that point, and then you can imagine that the slope of the secant, because in principle this is a secant, when I zoom in, right, I have 1 point here and 1 point here, I determine this slope. This is a secant. But what I want is basically, I can now move this point up towards this one, or that point down to that one. So let's move this up here, right? So that's my next secant, this is my next secant, and that's my next secant, and this is my next secant. And at some point, right, I get the tangent. And this is the first derivative. Right? Do you get this? So you're shrinking these slope triangles. That's what you are doing here. So the real current at a certain point, and then you are evaluating this at a certain time. Let's say at the time t, let's say at the time t, I don't know, t1. So that this would be the time, the current at t1. What I mean here is you let, for example, or in this case, I use T2 anyway. You have to, this is a local, what I want to express here is that this is a local property, right? So this is the slope of the tangent you get. And the slope of the tangent depends, of course, on the time, right? So here the slope of the tangent is steep, here the slope of the tangent is flat, which means this is a local property. What do you say when you say the first derivative? Then I would ask you, at what point? Which tangent do you mean? This one. Or do you mean this one, right? So this here, you can, for example, move this point. So delta t towards 0 means move t1 to t2. And then you get the secant, the slope of the tangent at T2. So maybe I should rewrite this. What I mean is, when I say the limit of delta t approaches 0 of q, what is it, T2 minus q of T1 divided by T2 minus T1. And now I can decide delta t is the distance between them, right? So I can say this is basically delta t. So I can let T1 approach T2 or T2 approach T1, right? So for example, I define it now. What I want is I want to move point T1 towards T2. Right? I move this point to that one, and then finally I get the slope at this point. T2 minus T1. I hope that this is clear, right? And if I let T2, what happens if I let T2 approach T1, so the other direction? I would get?
No, if you get T2 other direction.
Yeah, so look at this, right? So in one case, so in my case, I move T1 to T2. And if you do the other way around? Right, I would get the slope here, right? So that is basically, you have to think, where? So if you do it like this, T1 approaches T2, then you say, okay, this is then the current at T2, right? So I move this point towards that one, the secant, the slope of the secant becomes the slope of the tangent, but where? Since this point here is approaching this one, I get finally the first derivative at this point here. This is how it works. And you can even, you know all these derivative rules, how to derive a polynomial, right? X squared is 2x and so on. If you do this step by step, you will find out this works. Right? So you can do this even, you can prove it, not prove, but at least you could support this approach here. Okay. So you see, I hope that you now understand what this means. Probably already knew, right? But maybe kind of recap. So this is the slope of a triangle, the secant, right? And if you make it smaller and smaller and approach, so you move one point to the other in the time, you get the real derivative. So this is an approximation, right? So you can stop at some point. You say delta t, I don't drive it to 0. I go from, let's say, 1 second to 0.1 second. So I shrink it, and then I still have here a slope of the secant, but you can imagine that if delta t is small, you have a very good approximation for the first derivative. That is what you're also doing in numerical mathematics, right? When you solve such problems numerically, you are always working with, let's say, limited temporal resolution of your points. Sometimes it's good enough just to take 2 q's and 2 t's. If these q's are very close and the t's are very close, then this is a good approximation for the derivative. Okay. Oop. Good. So I hope this is clear, right? Q's transported through a cross-section, which is a kind of control cross-section, counting the Q's per second. Okay. So then we have an example here. So what is the average current involved when a truck battery sets in motion 720 coulombs of charge in 4 seconds while starting the engine. 180, right. Because it's, how do you calculate?
720 divided by 4.
Genau. So 720 coulombs divided by 4 seconds. Coulomb per second, right? That's the current, which is then 180 amperes. So how long does it take 1 coulomb of charge to flow from the battery? Is this clear, the exercise? So there's a battery, you have a truck, and this battery, you have an electric motor, which then turns at the beginning, which has to turn your combustion engine until it starts and runs on its own, right? But in the beginning, you have this electric motor which turns this, and that really consumes a lot of energy. So 720 coulomb in 4 seconds. How long does it take to discharge? If this is the current, as Jonathan said, is 180 amperes, coulomb per second. And now the question is, how long does it take to discharge or to transport 1 coulomb from the battery?
1.5 milliseconds.
Okay, are you sure?
1 over 180 seconds. 1 divided by 180 seconds.
So let's see. This is clear, right? Delta Q divided by delta T, 100 amperes. So now we have to solve this for the time, right? So delta Q would be 1 coulomb. The time is what we are searching for, and the current is the current we determined here. 5.56 milliseconds. Okay. Good. So we will see, this is now an actual charge curve of a capacitor. Right? This is the charge curve of a capacitor. We will discuss it later. What is a capacitor and how does this really happen? Why is it like this? We do this later. But we anticipate that this curve here is an exponential, which is, so here this 1 minus, oh, I think I have to explain this a little bit more. Okay. Okay, let's talk about exponential functions. Not too much. So what is particular about so let's say f of x is e to the power of x, right? The simple one. So for example, a to the power of x is also an exponential function. Okay, e to the power of x. E can also be seen as a number, right? Do you remember what this approximately is? Approximately 2.7, right? Can you give me some more decimals? How large is this number? But 2.7 is good enough. Okay. Okay, so let's say this is x. 1, 2, 3. 1, 2, let's say 3. 0, of course, is the origin. And then here the negatives. So first of all, what is f of 0? 1, right? E to the power is e to the power of 0. Any number to the power of 0 is 1. It's this point. What is f of 1? Okay, right, it's e to the power of 1, which is approximately 2.7, right? So this is a non-periodic number. How do you say? All right, it's not a non-periodic number, so there are several more decimals, of course, an infinite number of decimals. So it cannot express, it's not something like a divided by b. It's not a rational number, it's an irrational number. It cannot be expressed as a fraction. Okay, anyway, so that would be maybe this point here, right? What is d over dx of f of x? Is, let's say, the derivative. So sometimes we also say f prime, right? Are you familiar with this? What do you prefer, this difference quotient or? Is this clear? Okay, so this is e to the power of x itself, right? Aha! What is this? What is this f prime? This, how can I draw this? What is the first derivative? The slope of a function. Does it change with x? Yes, of course it does, right? The slope of the function depends on where you are. When I am at 0, what would be the slope? 1. So how does that look like? The slope of 1 looks like this, right? This is f prime of x at is 1, right? At 0 basically, right? F prime evaluated at 0 is 1. Which means, yeah. Okay, let's go on. We need another point. What is f of negative 1? Is e to the power of negative 1, right? How can I rewrite this?
1 divided by e.
1 divided by e, which is 1 divided by 2.7 something, right? How much is this approximately, or do you have a pocket calculator?
0.367.
So that would be here 0.3, so it's approximately a third, which would be a third, right? So it's something like a third, approximately. So a third, maybe 3/6, maybe here, right? So that would be this point. Okay, so now we have 3 points, and we have the slope here. So that means we can draw this thing like this one. What is the limit of e to the power of x as x approaches infinity? Infinity, right? That grows beyond all measures is infinity. So it's equal infinity. So approaches, let's say it's approaching infinity, right? And what is the limit of e to the power of x as x approaches negative infinity? 0, right? Okay. Can f of x be less than 0? No. Right? This is positive. It approaches here 0, here it approaches infinity, here we have a slope of 1, this is an exponential. How does the logarithm look like, the natural logarithm? How can I derive the graph of a logarithm from the graph of an exponential? Okay, let's make another example. I have a function y is x squared, which is a function of x, right? Right? So 1, 1, 2, 1, 2, and so on. This is x, this is y. X to the power of 0.
0.
Sorry, 0 to the power of 2. 0 to the power of 2. 0. 0 to the power of 1. 0 to the power of 2. 9, 3.
0 to the power of 4.
0 to, sorry, oh my God. 2 to the power of 2. And 1/2 to the power of 2. 1/4. What is the slope of this function at 0? 0, right? It's flat. Here it's flat. And it's symmetric. Okay. How does... This is my first function, right? Now I have another function. And the other function is x is y squared.
Just fix it.
Okay. Is this a function? No, it is not. Because for one x value, we have two y values, right? This is not a function. So you have to decide. So basically, what this is, of course, is then the square root, right? So y, now you have to decide. Y is either plus square root of x, or y is minus square root of x, right? So you can use this branch, or you can use this branch to make it a function, right? Okay, but if you look at these graphs, how are they related? Yeah, I would say, you can say rotate, but no, they are not really rotated, they are mirrored. Because when you rotate this positive branch here, you would end up here. What you do is you are mirroring it about this axis. You flip the graph about this axis. Right? So I take my piece of paper, and I fold it here. Right? And then I have it. Okay? So how do you think this is, what does that have to do with the logarithm? So what is the log? The principle is the same, right? We are now mirroring the initial function, the exponential, about this 45 degree line, right? So this point would be mirrored here, and this one would be, where is it? Here, right? Yeah, I think here, and this one here would be mirrored here, right? This is DLN. Okay? So now let's think. What is ln of 1?
0.
You immediately see this here. What is the limit of the ln x if x approaches infinity? Infinity. What's the limit of ln x for x approaching negative infinity? We're coming closer and closer to 0, right? Which is not true. not defined, right? We cannot go with x to negative. This is not defined, right? The negative numbers do not belong, numbers do not belong to the domain of the logarithm. But we can say, what is the limit of ln x as x approaches 0? Negative infinity, right? Okay, like this. Good. Exponentials. How does now let's come back to capacitors. How does the function e to the negative x look like? Say here's 1, 2, here's 1, 0.5, 0.25, right, and so on. How does this function look like for positive x's? No. What is x of 0?
X equals 0 or 1.
1. F of 1. 1 over e is f of 1. This is 0.367, right? Where is this? Somewhere here. Somewhere here, right? So here. And what is EF of negative 2? Sorry, plus 2? 1 divided by plus, right? E squared. How much is this? Can you take a pocket calculator? 0.14. So it's somewhere here, right? So you see this is decaying. And this point here is important. This is the 1 divided by e, right here, which happens after 1. So you can say that this function decays by down to a third approximately, which is approximately a third, right? So 36%. It decays. So it starts at 1, let's say 100%. And then this function decays down to, let's say, 36 or 37% when x is 1. We will see this later when we talk about charging and discharging of capacitors. Okay, new functions from old functions. Let's start with a parabola. Something like this. X, f of x, right? What happens, and this is, here is 1, and here is 1. F of x is x squared, right? What happens if I define a new function, f of g is negative f of x?
Mirror around the x-axis.
I would mirror it about the x-axis, right? So I need now a few colors. Let's say green. I don't know if you can see green. This is green. And it's here and here. So that means when I multiply this with a negative number, so it's -1 basically, right? So this is times minus, so g of x is -1 times f of x, right? So that flips the graph about the x-axis. What happened if I changed the value? Let's say I would use, let's say I have another function, let's say f2 or so, which is c times x squared. So if c is negative, it flips about the axis, right? And if c is positive and larger than 1, what would happen?
Change the amplitude
Yes, and how?
by the vector c.
Yes, that's true. Amplitude is maybe not the right way, the right word, but instead, let's say c is 2. Let's say f2 is 2 times f of x. So then I would have, instead of the 1, I would have 2, right? And instead of 0.1/4 here, I would have 1/2, right? Which means this so if c is greater than 1, it stretches the curve. It simply stretches it, right? It squeezes it together. It looks as if it were squeezed, but it's stretched. And if the magnitude of c is less than 1, but greater than 0, what would happen?
We put it together.
Is this clear what we're doing? So what do you think if c is 0.5, for example, 1/2, what would happen? Exactly, right? It's as if you pushed on it and you would stretch it. Or compress it, right? It depends. Right? Maybe it's compressed, right? Here we are stretching. If c is greater than, if the magnitude of c is larger than 1, we would stretch, and otherwise we compress. And then it can be positive or negative, so we can flip it downwards, and stretch and compress. Okay, what happens? Now I have my g, I need another function. I should have chosen other symbols. Okay, now I have h. h of x is g of x plus 1. What happens now? I just move everything up, right? I don't stretch or compress, I just move it up. Which means in the end, the function looks like this. No, it's not true, right? There's one more here, like this. Here it's flat. Great. And then it can also be shown that we can move this left and right. Now I don't know, I need another function name. Maybe m. m of x is h of x minus 1, for example. What now happens is, when you subtract here a number in the argument, you move it to the right. Because what used to be h of 0, it's this point here, this is h of 0, right? That occurs later. You have to fill in x is 1 to achieve the same point. Which means what used to be h of 0 is now h of 1, right? Which is then here. You know what I mean? So, for example, when you fill in x so h of 0 is 1. It's this point, the apogee here, what do you call this? Forgot the name. Vertex. Right, this vertex. And now, when I add here, if I use now x is 1, 1 minus 1 is 0, I get to the same vertex, but that does not occur at 0, it occurs at 1 here. So you shift it to the right and to the left. This is new functions from old functions, so you can shuffle them around. Now, how I would like you to create another function which pretty much looks like this one here, but it's kind of flipped, like this. How can I create this red function from the black function? You know what I mean? They are symmetric, right? About this point and everything.
The 1 minus the function.
Exactly, but can you tell me why?
Because at 0 point, the function starts at like 0. So if we have 1 minus 0, we start at the top of it. And then we are increasing the amount we subtract from 1, so it's decreasing.
That's true, but I want you to use these geometric identities or the geometric development of this function. So what do you have to do first? So negative, absolutely. We multiply it by 1, we flip it about this axis, and we get this curve here. That's the negative e to the power of minus x. And then what you said, now we lift it by 1 because we don't want to start at negative 1, we want to start at 1. Do you get it? So the red curve now is, let's say, the g of x is, we start with our old function, we multiply it with negative 1, and then we add another 1. And this function is super important. Both of them are super important. First of all, this is a typical decay you have in nature, right? We will talk about this later. This is a decay function, and this is a kind of saturation. Something saturates. And you can think of this factor here being kind of percentage, right? When you, for example, discharge a capacitor, you start with 100% of your charge, and then it drops, right? And then you have at some point 0 charge. Okay, in fact, you wouldn't reach it mathematically, but physically, yes, it would be 0 at some point. And this is the charging curve, or a saturation curve. And this is always, so these curves always occur if the process, the rate of change, is dependent on the current state itself. And we will do this probably when? What time is it? Okay, maybe let's have 5 minutes break. And then, how long? What did we say? 12:30? No, 11. Oh, okay, 5 minutes break and 11. When do we stop? What do we say? 11:30, right? And then we continue at 12:15, right? So let's have 5 minutes break and then we continue until 11:30. Okay.